Hi everyone. In the previous lecture, we discussed about the McDonald's idea of dividing a region into small cells so that with just a finite number of channels S, we could cater to a very large number of users. So using the concept of frequency reuse and cell splitting. So these are the two ideas we have discussed in the last lecture. Now McDonald did not just stop with that. He said, okay, that's a theory. Now you divide it into cells and then you can then accommodate more number of users by concept of frequency usage. He didn't stop with that just as it is. He actually gave a proper rigorous mathematical analysis to say that the instant we are going to go for frequency reuse, so which means we are reusing the same frequency in a different cell, then the problem was that there is a problem of interference. So for example, I've shown in this figure that the frequency channel A is being used in 5 different cells. Okay, it's used here and it's used here. Now all these cells, for example, a cell phone which is present in this cell, okay, will receive signal power from all these channels because all are transmitting in the same frequency channel. Okay, so I can receive power from all these channels and these are called interferers. Now the question is, what should be the frequency reuse distance? I mean, what should be the distance after which should I reuse my frequency? And what are the problems of reusing the frequency itself? Okay, so there is something called interference, and how do you quantify interference? So that's something that needed to be answered. So once we go for the concept of frequency reuse and dividing the region into cells, we are going to end up in the problem of interference. Now interference will also act like noise. That's what we discussed in the last lecture. So which means first we need to have a good estimation of what is the carrier, the signal to interference ratio. Not just signal to noise ratio. Now signal to noise ratio, you need to know the internal circuits to compute that. But for as communication systems is concerned, we assume a certain noise level and then do our calculations. Okay. Now for SIR, signal to interference ratio, we need to be able to at least get an estimate of what is that before we start designing a communication system. So that problem was also answered in a mathematically rigorous way by McDonald's. The McDonald's paper had answered it. Now the question is, now he said, okay, we are going to divide a region into cells. What should be, for us to have a ease of good mathematical analysis, what should be the shape of the cell should I choose? Okay, so that's the question that he had started with. Now any given region, I'm going to fill that region with cells. I'm going to divide it into cells and I'm going to fill that region with cells like this. Now the question was to have a good mathematical, tractable and simple mathematical analysis. He wanted to have a certain shape of a cell for that region. Okay, what should be the shape of the cell? Now first, let's say the easiest one, because an antenna radiates. If you take a base station antenna, it radiates in a circular pattern, meaning most of them are omnidirectional antennas, so they'll have equal radiating power in all directions. Okay, in the azimuthal angle direction. Now if that is the case, then the ideal choice would be a circle. But the problem with the circle is, when you're going to populate an area with circles as your cells, they'll have uncovered regions in between. I'll have uncovered regions in between, and then to resolve these uncovered regions, then I need to have overlapping. I need to put these cells as overlapping cells so that I don't have any missed out regions like this. But that was not a preferred solution. Once you overlap, you don't know what is the actual interference, what is the overlap distance and all that. It becomes too complicated. So instead he wanted to choose a polygon, a regular polygon, okay, because they all have to look identical in all directions. So the only easiest option is a regular polygon. Regular polygon is any polygon of n sides where n is obviously greater than or equal to 3. So you start from triangle, square, pentagon, hexagon and so on. Okay, so n should be greater than 3. All the sides of the polygons are of same dimensions. Okay, then that's called a regular polygon. So now the question was, what should be the regular polygon that he should choose? So that's the next question he had started with. Now we know that the problem with going for circles, though they were ideal, was that they were having regions which it could not cover. They didn't have a complete, they wouldn't, if let's say I'm going to fill a region using circles, there were some regions which will not get filled out. So the polygon that I'm going to choose should be such that if I replicate that polygon throughout that region, there should be no empty spaces in between. It should fill out that region without any empty spaces. Okay, so which means, let's say I take a polygon of n sides and I'm going to replicate it. So when let's say a polygon of n sides, I'm going to replicate it, it should have no space in between. Now how do we ensure that? What we need to do is every polygon will have an edge, okay, which is the point, the intersection of two sides of a polygon joined together to form an edge. Okay, now if I'm going to replicate this polygon like this, okay, so this is one edge, this is one edge, this is one edge, and this is one edge. All the four edges should completely span 360 degrees. Okay, they shouldn't have any gaps in between. They should perfectly, when I'm going to place, so this is polygon 1, polygon 2, polygon 3, I'm showing only the edges of the polygon. It should be ensured that for this example I've taken 4 edges of the polygon, they should form a perfect non-overlapping region. Okay, and there should be no space left in between. Okay, so I'm going to take a polygon, repeat it 4 times at an edge. I'm going to at near the edge, I'm going to repeat it k times, I'm going to repeat it k times. Then if I repeat it k times, the angle formed by all the sum of the angles of all the edges should be equal to 360 degrees. If I ensure that condition, then I know that I'll be perfectly filling out a region without any empty spaces. Okay, so first we need to know what is the angle of an edge, what is the angle arced or angle spanned by an edge in a regular polygon of n sides. So let's say here I've shown in this figure, I'm going to draw from the center of the polygon. It can be anything. I've taken an example of hexagon here, but it can be any polygon. So first you can draw 2 lines joining the edges. Our goal is to find this angle here, this entire angle. Okay, so if I show it here, I need to find this angle. Now to find that angle, what we can do is, first, because this is a regular polygon, it has n sides, I can divide this polygon into n sectors like this, into n regions like this. So each angle here will be 2 pi by n. They will all be equally split. It's a regular polygon, so which means all the sides are equal, so the angle will also be equal. So which will be 2 pi, which is 360 by n. Now here I need to find this angle, that is nothing but this angle here is also theta, but if theta is the angle spanned by an edge, then theta by 2 is half of it and half of it here. So to find theta, I just have to find the sum of these 2 angles, this angle here and this angle here, which is same as this angle here is same as this as well. So the sum of the 2 angles there, theta, it's using the triangle inequality, means a triangle, so sum of the angle should be 180, so pi minus 2 pi by n, that will be your theta. Now we have argued that if I take a polygon, okay, and I'm going to place those polygons adjacent to each other, so which means there will be 2 edges are going to overlap. Okay, the 2 edges are going to be placed very close to each other. So the angle span, this is theta, by another polygon is theta. The sum of all the angles, I'm going to replicate it k times. So k into theta should be equal to 2 pi. That's the condition I have to satisfy. For this polygon to completely fill out that region without any empty spaces, I need to satisfy this condition. K theta should be equal to 2 pi. Now theta is again pi minus 2 pi by n. So I'll equal to 2 pi. If I substitute it, I get this result. Okay, I've just cancelled out pi from this equation. I get this result. Then if I rearrange the terms, I'll get 1 by k equals 1 by 2 minus 1 by n. This is a very, very important result. So to understand this, why did he choose the geometry that he chose? It's a very useful mathematics to follow. So 1 by 2 minus 1 by n equals 1 by k is the equation I get. Now we know that k is an integer because I'm going to repeat my cell an integer number of times. So I should not have any overlaps and all that. So I have to, this is already, we began with the assumption there are no overlaps, which means I have to repeat it integer number of times. Okay, so the values, permissible values of k are 0 means it doesn't make any sense. I have to at least repeat the polygon once. If 1, again it doesn't make any sense, you have to repeat it more than once. Only then you have, you can say that it's actually a polygon which can be, you need more than one polygon to span out that region without any empty spaces. to fill out that region without any empty spaces. So let's assume 2. So I'm just going to put 2 polygons and see what is the value of n I get. If k is 2 here, the value of n I'm going to get is infinity. Now what is n equal to infinity means? It means the polygon actually is a circle. The polygon actually becomes a circle. The angle that it spans, if I keep reducing n for a regular polygon, if I keep increasing the value of n, the length of the side keeps becoming smaller and smaller. Eventually it will become extremely small, the side. So then the polygon will approach a circle. Okay. The problem we already saw with the circle is that at the point where it joins, yes, of course, when the two circles join, you are not going to have any empty space here just at that point. But unfortunately, we know that when we're going to fill the the entire region with circles, we are going to end up having empty regions. Okay. So I'm going to rule out that solution as well. N equal to infinity is not a feasible solution because it's a circle, so we are going to rule out that solution. The next solution is k equal to 3. So we began with k equal to 0 is not possible, 1 is again not a possible solution. Now 3 is the next thing. If k is 3, you get n as 6. Now see here, I just jumped from one value of k equal to 2 to k equal to 3. N value reduced all the way from infinity to 6. So which means the next value after infinity which will satisfy this inequality is a hexagon. Okay. So that's the largest polygon which will satisfy this equation. Okay, because n is reducing now, so largest polygon size regular polygon which will obey this equation. Now the next value of k is k equal to 4. If k is 4, then you get n as 1 by n is 1 by 2 minus 1 by k. If k is 4, you get 1 by 4 n as 4. In that case, it is square. Again, polygon should make sense. So if let's say we take a polygon, so this angle is 120 degrees for a polygon. Okay, so I'll put another polygon here. So this angle is again 120 and I form a third polygon here 120 degrees. So I just have to replicate it thrice to fill out this region without any empty spaces. Okay, there will be no empty spaces in between. So I get hexagon. If I repeat it 3 times where k equal to 3, then I fill out that region. So similarly for a square, I'll have to repeat it 4 times. I'll have to repeat it 4 times at this point, then I will not end up having any empty spaces in between. Okay, so you get n equal to 4 and k is also equal to 4. I have to repeat it 4 times for a square. Okay, now the next thing, k equals 5. Okay, so if you see, n is actually a decrease. N is the value of n is decreasing now. From 6 we went to 4. So in between we had a value of 5. 5 is not a feasible number. You can try it yourself. 1 by 2 minus 1 by 5 is 1 by k, and k will be a non-integer here. You will get it as a fraction. So the moment we get it as a fraction, we discussed that there should be no overlaps, which means this is not possible solution. Okay, k has to be an integer. Okay, so now k equal to 5 is again, we'll see what happens when k equal to 5. You get n as a non-integer number, so k cannot be equal to 5. So we cannot repeat any polygon 5 times and then expect us to fill out that region. So that no such polygon exists which will obey this condition. So k equal to 5 is also ruled out. The next was a possible value of k is k equals 6. Okay, so in that case your 1 by n will be equal to 1 by 2 minus 1 by 6, and I'm going to get n as 4 by 12, which is 1 by 3. N equals 3. Okay, so now we have gotten a triangle. So if I take an equilateral triangle and I need to replicate it 6 times. Okay, so I haven't drawn it properly here. So this is 60 degrees. I have to replicate 60, 60, 60 and 60. So I think I've missed one more angle, so it should be 60 and 60. So if I replicate tessellate a triangle, tessellate means just repeating it over a structure again and again, over a space again and again, the same structure. So the equilateral triangle will also form with k equal to 6. It needs 6 repetitions at that point, at any point, to actually span out that entire region without any empty spaces. So now if you see the minimum value of n, we said n should be greater than or equal to 3. Okay, and the maximum value of n that obeys this condition is n equal to 6. Now out of which we have to rule out 5 because 5 doesn't obey that condition. So the 3 values of n which obeys this condition 1 by 2 minus 1 by n equals 1 by k, where k is an integer, okay, are 3, 4 and 6. So this is a triangle, a square, and this is a hexagon. Okay, so these are the three geometries which actually obey this condition. So that's when we start with the three geometries here, which will perfectly span out this entire region, which is a triangle n equal to 3, n equal to 4 and n equal to 6 in this case. Okay, so these are the simple regular polygons which can fill out without leaving any, fill out an area without leaving any gaps. Now among these polygons, which one should we pick? That was the next question. Now to understand that, what we can do is, first let's inscribe the polygon inside a circle by drawing a circle of radius given by the radius of, for example, you start from the center of the polygon and draw a line to the edge, and then inscribe this polygon inside that circle. Now by doing so, what are we trying to do here is that we are, as we said, it's better to approximate the even intuitively you can say that if I want to pick an object among the three, I'm going to pick hexagon because it approximates circle to the best possible way. Okay, in a best possible way it approximates a circle. And why did we choose it has to approximate a circle? We said the reason being the radiating antennas are mostly omnidirectional. So because of that, it's better to use a structure which will resemble a circle as much as possible. Okay, so to do that, if I try to inscribe a circle, this triangle inside a circle, and try to compute the area of this triangle and see how much of a fraction of the area that it's going to span within this in this circle, inside this circle. So if this is r here, this is also r, so this distance is going to be root 3r, and we know the area of a triangle is root 3 by 4a square, where a is root 3r the whole square here. So you will get 3 root 3 by r. So that's the result. So that is approximately 1.3 r square. Now we know the area of the circle is pi r square, which is nothing but 3.14 r square. Okay, so now if you see 1.3 is not even half of it, so it will be less than 50%, not even half. Okay, it will be around 40% or something, so that's the area that this triangle is going to occupy within this circle. Okay, it's going to occupy 40% area of the circle. Now next we'll go for the square geometry. Now if this is r, then I'll assume this is r. Now in a square, we know this angle is actually, so this is 45, 45, so this angle will be 90 degrees. So if this is 90, this will be root 2r. Okay, so if this is root 2r, the area of a square is going to be 2r square. Now if you see, the square is going to occupy approximately 2 by 1.3 by 3 by 3.14. Now that is close to 60 degrees, 60 to 65 degrees, something like that. Okay, so which means it is around 60 degrees, 60% of the circle's area will be occupied by the square here. And finally, when we go for the hexagon's area is going to be root 3 by 4 r square, because I can divide hexagon into 6 equilateral triangles, each with a side of r. So root 3 by 4 into r square times 6. So that you will get it as 2.6, which is almost twice the area spanned or occupied by the triangle. So you get 2.6 r square. That is around 80% of the circle's area will be occupied by the hexagon. Okay, so obviously by this logic itself, I should pick hexagon. So, and there is again a very simple theorem that you take any given area, and you want to span it out, you want to fill it out using geometric shapes without any empty spaces. We said there are three possible shapes: triangle, square, or a hexagon. The hexagon is going to take, because if you see, if I picturize each area as a circle, hexagon, you will need to fill this region using the least number of hexagons. Okay, so if I want to pick between these three polygons, then any given region can be entirely filled out using the polygons. The minimum number of polygons necessary will be for a hexagon. Hexagon will just need the minimum number of polygons, which means I can also use the word called they have the best packing density. Okay, you will just need the least number of hexagons to fill out a region without any empty spaces, which is why nature by its default tends to choose hexagonal shapes whenever necessary. So this is a classic example where what I've shown here is the beehives. Beehives naturally tend to form a hexagonal shape like this. Okay. Again, they want to optimize the number of spaces where they have, and in a given area they have to fill it out, because again, see, they need some effort to build that. So you have to also always ensure you are going to build the minimum number of shapes. So beehives naturally tend to form hexagonal shapes for this reason. Okay, so it's the most optimal structure that you can go for. In a given area, if you want to fill out with a polygon with minimum number of with minimum number of polygons without any empty spaces, then hexagon is the choice to go for. And that is the reason why hexagon was chosen for analyzing for the shape of a cell size. The cell size will be hexagon in our analysis. Now, in our analysis, we will also assume that the antenna is located at the center of the base station. The base station is located at the center of the cell. Okay, the cell radius is r here, and the base station or the cell site, okay, is located at the center of the cell, and your mobile station is allowed to move around the entire hexagonal cell. Okay, sometimes in some analysis we can also analyze it with antenna being at the center of an edge. Okay, at the center of an edge. So in that case, I may have the region of coverage will normally be we may have to draw a smaller hexagon like this, which will cover here. You can picturize that way, antenna radiating within a smaller hexagon, each antenna. Okay, I move half the distance and draw a line. I mean, you can construct a hexagon by doing this way. So between these 2 points, you can draw perpendicular lines like this, and let all those lines join. I think you will get a hexagonal shape. Okay, so you will end up having a hexagonal shape. So I may not have drawn it properly here, but you can get that. So you can actually draw a hexagon around this. But we will be choosing this for our analysis in this course right now. Now, because we are going to use hexagons, it's better to have a good understanding, a mathematical understanding of the hexagonal geometry. How do we analyze hexagonal geometries? Now, first thing is, the very important parameter of interest to us is distance between two base stations, because the distance between two base stations is going to dictate what we call as the interference ratio, carrier to interference ratio. Okay, it's going to tell us how in fact the two very important parameters is, one is the cell radius r, the other parameter is the distance between the two base stations t. Okay, now here I have taken the nearest adjacent base stations. What is the distance d between the two adjacent base stations? Now you can just use the triangle inequalities to solve this problem. So this is r here and this is r. So this distance is going to be d by 2, and since I have equally divided this region, this length is going to be r by 2, and this angle is 60 degrees. So from that we can show that your d by 2 divided by r by 2 is tan of 60, which is root 3. So your d will be equal to root 3r. Okay, d will be equal to root 3r, and the ratio d by r will be equal to root 3. And here you have to be very, very clear here, the d is the adjacent cell distance right now. But typically when we see the analysis later, we use the word called reuse distance. It will be distance between one cell center to some other cell center. Okay, so that will be your d by r, which is root 3. Now if I assume d as 1, if the distance between two base stations, I am assuming it has a unit distance is 1, in that case r will be equal to 1 by root 3. Okay, so with that assumption, I can assume that r will be equal to 1 by root 3. Okay, if I assume d as 1, the distance between two cell centers as 1. Okay, I'm sorry it's a little noisy here, but I can't avoid it now, so we'll just go ahead with it. So the next thing is that we will talk about some properties of hexagon. The properties of hexagon, meaning again these will help us in analyzing the distance. Eventually we are more interested in the distance between the two cells, centers of the two cells. So how do we analyze it? Sometimes we'll encounter distances which might be a part of a hexagon. So but that's why understanding hexagon helps us in that sense. Okay, so one thing is we are supposed to find what is the distance between the center of two edges. So this is one edge and the one other edge. What is the distance between the center of two edges? and that will simply be equal to d. In fact, you can actually draw another hexagon like this. So you can draw another hexagon like this, and this center, the distance between the two centers will nothing but be d. We already know that, and that is same as the distance between two center of the two edges. Okay, and you can very easily show that result. So we know this is r here, and if this is r, okay, and this is r here. So in fact, we have already shown this distance is nothing but d by 2, because you can actually have another hexagon on top of this, and that distance will simply be d by 2. I'm sorry, I think that's very, very trivial. So this distance from center to that, it's same as this distance. So this is d by 2, this is also d by 2. Okay, so this is d by 2, and the distance between this center and this center here will be d. Okay, and similarly, if I draw a line here, a line joining the two edges, okay, a line joining the two edges, that distance will also be equal to d. Okay, because they are all parallel lines here, so they will be d. That is also d. Now the next thing is again the distance between the center of two edges. So this is d by 2, and that's the maximum distance. So d is in this case root 3r, which is 1.732 r. Now we will see other edges. So for example, distance between two adjacent edges. If I want to find the distance between two adjacent edges, then that is going to be d by 2. Okay, that's because if I start here, what I've shown here is that, so let me show it in this hexagon here. So this distance, the first hexagon, so this distance is d by 2, this distance from here to the center is d by 2. So similarly, I can draw 6 such lines. This angle is going to be 60 degrees, and this distance between the two center of the two edges will also be d by 2, because it's an equilateral triangle, and all the sides are equal, so that will be d by 2. The other distance between the center of two edges, shown in the blue line here, is the distance between the two, not the two adjacent ones, but the one after the adjacent one. The center distance between the two centers, the edges of the center edges, okay, will be 1.5 r. Again, this is something you can very easily derive. So this is d by 2, this is d by 2, this angle is 120 degrees. So this is simply root 3 times d by 2, okay, and d we know is root 3r, so you will get 3 by 2r, which is 1.5 r. That's the blue line shown here. Okay, so that's the maximum distance between the two center, the edges of the maximum distance between two centers of the edges is d, okay, which is 1.732 r, and the next one is going to be 1.5 r, which is the distance between the one edge and the edge after that, okay, non-consecutive edges, is going to be 1.5 r, and the distance between two consecutive edges, two adjacent edges, the center of the two adjacent edges is simply d by 2, so that is 0.5 r, 0.5, sorry, it is 1.732 by 2 r, okay, so around 0.8 or something. So then after that, we are now interested in finding the distance between the edges itself, the distance between two edges in a hexagon. And the easiest one shown here in blue is the maximum distance between two edges. That will be simply the radial distance, which will be 2r. Okay. The other edges, which is nothing but the shown in red here, which is one line which is shown here, and we already discussed that is same as the distance between the center of two edges, because they are two parallel lines. So this we know already is d, and this is also d. Okay, shown in blue there. So they are all d. Okay, so they are the distance between two, shown in red. I'm sorry, it is shown in red here. So this distance d here is, let me show it in red. So this distance d here is root 3r. Okay, it's distance between two edges. Okay, and the distance between the two largest edges, farthest edges, is 2r. So the values you will get here is 1.732r, 2r, okay, and obviously the distance between these two edges is r. Okay, again I've already discussed this problem in the class, so you're now supposed to find, using whatever simple analysis that we have done so far, the distance between the center of this to the center of all these cells shown here. Okay, the radius of the cell is r. It's given that the radius of the cell is r, the distance from center to one of the edges is r. You have to express your answers in terms of r. So quickly, if from 1 to 2, if you see this distance is d by 2, this distance is d, and this is d by 2, so it is 2d, which is nothing but 2 root 3r. D is simply root 3r. Here again, it might be confusing here. D is nothing but I'm just calling the distance between two adjacent centers of the two adjacent cells as d. The definition of d will be different later. Okay, so right now for our discussions I'm just assuming it as d in this problem. So that's 2 root 3r. Next one is 1 and 3. Between 1 and 3, if you see, to reach this point 3, again we will use a regular orthogonal coordinate system, 2D coordinate system. So to reach the point 3, I can move in this along this direction and another perpendicular direction to reach this. By choosing this approach, the distance between 1 and 3 can simply be found using Pythagoras theorem. So if I move along a two-dimensional Cartesian axis, I can simply use Pythagoras theorem. I've moved x units along this axis, y units along this axis, or I'm calling this as x-axis and this as y-axis. Okay, or you can call it the other way as well. It will be simply root of x square plus y square. So you just have to find what is this distance which is moving along this axis. So this is d by 2, d and d. So you get 2d plus d by 2, which is 5d by 2 the whole square, plus this distance. So this is r by 2 and r, so that will be 3r by 2 the whole square, with the square root. Okay, 1 and 3 is that, and that can be easily found. So your 5d by 2, d is root 3, so it's going to be 25 by 4 into root 3. No, 3, sorry. Okay, so 25 by 4 into 3 the whole square plus 9 by 4. So again you can find this result yourself. So similarly for 1 to 4, this distance is r, this is r, this distance is 2r, and this distance here is r by 2. I think that turns out to be 4r plus r by 2, that will be 9r by 2 the whole square, plus this is d by 2, so that is nothing but root 3r by 2 the whole square, and take a square root of this. And finally 1 to 5, this is r, and this is r, so which will simply be 3r. Okay, so that's the answers that you will get. So 1 to 5 is 3r, 2 root 3r, and you'll have to solve these equations and you get root 21r for each. Now the problem with having a simple Cartesian coordinate system and then trying to find the distance between 2 points, two cell centers, is that in a real system, for example, if you take a cellular phone system, when we are trying to find, let's say usually we will be interested in finding the distance between two cell centers. That's a very important quantity of interest. Now if I want to go to any cell center, I can move along the cell centers, along the directions of cell centers itself. So I can move in this direction. Let's say I want to reach this point here, this cell here, I can move 2 units in this direction and 1 unit in this direction, or 1 unit in this direction and 2 units in this direction. Okay, or I can draw 2, 1 and 1. Okay, so by moving, instead of moving in orthogonal axis like a Cartesian coordinate system, following a Cartesian coordinate system, if I rather instead choose an oblique axis. Okay, so now if you see the angle with which I can move from any cell to another center, it's in 60 degree steps. Okay, it's in 60 degrees, so I'll have to move by 60 degrees on each side. Okay, so then if I pick an axis which is 60 degrees apart instead of 90 degrees, it becomes a lot more easier in analyzing these problems. Okay, then I don't need to talk about in any other terms except the distance between the two cell centers. That will be my unit of measurement. Okay, if I call that as 1, then the cell radius is going to be 1 by root 3, if you recall from the previous lectures. Okay, if you recall from what we discussed a few moments ago, the cell radius will simply be 1 by root 3. So this new coordinate system is what we call as the UV coordinate system. Now in the UV coordinate system, this is a little so let's say in a UV coordinate system I have a point I comma j. Okay, let's say I have a point I comma j. Now this is measured in UV units. So to reach that point I have to move I units along this direction and j units along this direction. Okay, I units here and j units here to reach that point. Now to find the distance in terms of I and j from the center, assuming this cell where I've started from as a center, to find the distance I'll have to resort to using parallelogram law of vectors. Okay, so then that is simply going to be the length along the I axis is I, so the magnitude is going to be I square plus j square. In a Cartesian coordinate system it's simply I dot j. In a Cartesian coordinate system, or let me write it as 2I dot j, it is actually 2 into I dot j. In a Cartesian coordinate system, it is actually 2ij into cos of theta. If I and j were points in a Cartesian coordinate system, the distance from center to that point is going to be this. In any general coordinate system, theta is in any general coordinate system, this is going to be the expression. In a Cartesian coordinate system, theta is going to be 90 degrees because you will move in 90 degree angles. So this will simply be root of I square plus j square. Okay, and this result for a oblique angle system with this angle of 60 degrees, theta is 60 degrees, it will reduce to I square plus j square plus ij. That's what is written here. Okay, if you move I units in one direction, j units in other direction, then that point, the distance from origin to that center is given by this result. Now let's say we take a slightly more, little bit more involved case, which is I have 2 points u1 v1 and u2 v2. Okay, now we are supposed to find the distance between the 2 points. Now a Cartesian distance will simply be root of u2 minus u1 the whole square plus v2 minus v1 the whole square. Okay, but because it's an oblique angle system, these u1, u2 and v2 are measured using an oblique axis. This term will also come here. So again, that theta cos 2 cos theta is 1, theta is 60, so cos theta 2 into cos theta will be 1. You will get this additional expression, additional term. Okay, so this is the distance between any 2 points measured in the UV coordinate system. Okay, so finally, before we go to the analysis, in fact, this is all just the mathematical preliminary necessary to follow the analysis of a hexagonal cells in a cellular communication system. Okay, and a group of such cells is what we call as a cluster. So we have already discussed this. The whole idea was to actually take a region, divide it into small cells, and divide the cells, form groups of cells called clusters, and replicate many such clusters, and you can reuse the frequency so many number of times, which is so many number of times, which is equal to the number of times you replicated the clusters. Okay, so and we said with a finite number of channels, if I replicate the cluster m times, then the capacity, which is the total number of users you can support in the system, can blow up to infinity if m tends to infinity. Okay, so which is what we said. So in the next lecture, we will do a mathematical analysis of the cellular systems using hexagonal cells.